All right. Yes. All right. So we're not going to go through all this, but I just want to point out what happens if we do this alternate analysis. So what we're going to say is, what is the size of the nth group at time t plus 1? What's the expected change in the size, right? So this is the actual size at time t plus 1, the actual size at time t. And this is, on average, what we expect to happen. So we're going to allow that, the probability of replication could be, we'll get rid of this, but it could be something that depends on time. So you have to, for this to increase, you have to have replication to be chosen, right? So that's the first step. So with probability rho, something is, you get a new, unique, previously unseen element. This is the probability of replication, right? And then this is the probability that you choose the group you're thinking about here, because this is the size of the group and this is how many elements you have already. So it's this is a simple probability. If your group is size 904 and you have 10,000 so far, which is given simply by t, that's that probability. And then there's plus 1, right? We get one more in our group if that happens. So we don't have to worry about, we had that sort of delicate thing where groups of size n would become groups of size n plus 1, and we had to kind of play around with that balance, which was very nice. What a terrible machine. I don't like you either. Then there's this story. So the new guys only appear, right, at certain times. And so we have to think about when they appear in the system. So this is the nth group. This is its initialization, its time of arrival. So we have to think about that. If we play around with this a little bit, we get this simple kind of recursion thing. Don't have to worry about this too much. And of course, each group starts with a size 1. Now you can play around with that, but each group starts with a size 1. And this is really, that 1 turns out to be really important. I'll show you. So I'm just showing you some results here, and I just want to get the basic idea. So we've shifted the analysis, and it allows us to find this thing that was missing altogether. Sorry about that. What a frustratingly silly thing. Okay. Not that this is worth being recorded in history, but anyway. All right. Good. So we can get this kind of typical growth, and you see as time goes on, right, it gets harder for it to grow. There's always this factor of 1, which would just replicate it if you like, but this decays. Yeah. Okay. Go through all this madness here. You can play around with this. It's going to be sort of somewhat similar to some of the things you'll do, but you get out pieces. So this looks like, right, factorial kinds of structures here, and they're factorial-like, which turn out to be gammas. Don't have to worry about too much. But you can end up writing it like this, that it's beta functions, which are ratios of gamma functions. And really the key thing is going to be they all look pretty much the same, except the initial time when the nth group starts is really a key piece in there. So don't worry about this. Okay. So the issue is this. So for every group that appears, and this is what I was trying to sort of say here, every group that appears after that first one, the typical time that they turn up is going to be this, n minus 1 over rho. This is rounding that, right? So the second group typically, so 2 minus 1 divided by rho, right, is 1 divided by rho. That's the typical time that it would take a coin to succeed if its probability rho is success, right? And then 2 times that will get you to the second one, and 3 times that will get you to the third one. So we can just estimate that roughly. But of course, the first one just starts at 1, right? So this breaks down. We can't put n equals 1 here, right? That would give us a 0. We have to put 1. That starts at 1. So this initial condition really matters. And so Simon misses this because he looks at the size distribution. Right, we're getting out the rank distribution, the zip rank thing. We're going straight for it. He was looking at the size distribution. And if you look at the size distribution, there's this one, and you've got this, you imagine a Gaussian, right? So you've got a Gaussian, you have this infinity of things in here. And so if there's just this one little character out here, you could easily miss them. And if their size kind of shrinks in terms of how much they count for, then, and which is true over time, then you can miss them, right? So contribution of that first element actually vanishes, even though you can see how big it is. You get so many of these little ones that eventually it does decay to 0, but it's going to be gigantic. It doesn't apply to the Barabozzi-Albert model, which we will talk about in depth later on. This is one of the two most famous network stories from the late 90s that started complex networks. It's very similar, as I've mentioned. This is the preferential attachment story, very similar in structure to Simon's model, but it doesn't quite apply because there's always a new node there. Right. Just need to put that there so no one has a heart attack. Okay,